Hello everyone. Hello everyone on YouTube as well. So first of all, happy Navratri to everyone, and also happy Durga Puja. From today, Durga Puja festival is also starting. Next week it is Dashera, so best wishes for that festival as well. And today we are meeting for the 10th time in this course. This is the week 10 discussion, and today we will be looking at some examples about the product measure. But before that, let me give 1 minute or 2 minutes for audience to ask questions. So YouTube audience can ask questions on the live chat, and then we'll start. Okay, so if there are no questions, let me start with recalling all the things that we have done on week 10. So the basic problem was that given two measure spaces, given measure spaces x a mu and y b nu, where of course A and B are sigma algebras of measurable subsets. We want to construct a measure space x cross y, some sigma algebra S, and a measure eta. So the general method of doing this was x cross y, usually we denote it like this. So if it were both R and R, we would have denoted with the plane. So we continue using that notation to denote our x and y. So one of the axis is x, the other axis is y. And on this green line, I know how to measure we know what are the measurable sets. On this purple line, I know what are the measurable sets. I want to know what are the measurable sets in this sort of the plane that is formed by x and y. So this is not the actual plane. This is just a diagrammatic representation. What we want to do is, what are the simple sets that we can measure? Of course, singleton sets are the simplest sets, and we would like that the singleton sets should have measure to be 0. That is the best possibility that we would expect. But still, from the sigma algebras A and B, there are simpler sets that we can construct. Particularly, what we can do is, we can start with a set here. Let us call this set as E. We can start with a set here. So these are not intervals, they are just my representation of sets inside x and y. Now, set of the form E cross F, it looks like a rectangle. And this is precisely why I have made this representation, so that it is easier to visualize. Now, how to measure this? There is no direct way, of course, but one would expect that the area of a rectangle is length times breadth. Now, length comes from the measure of E, breadth comes from the measure of F, or the other way around if you want to call it. So, all in all, we would like that eta of E cross F should be equal to mu of E cross times mu of F. So eta of E cross F is mu E times mu F. Now, but then a set could be very well of this form. Well, it may not be a rectangle. It could be of this form, and then there is no direct way of measuring it because it is not the Cartesian product. We cannot say it is the product of some measures. So what we would rather do is to define the measurable subsets of x cross y. Let us look at the sigma algebra generated by all these rectangles. Sigma algebra generated by rectangles of the form E cross F, where E comes from A and F comes from B. And with this generated sigma algebra, we would like to define some notion of measurability, some notion of measure. And that is done by getting the outer measure first. So eta is defined on rectangles. This is the set of all rectangles. Then using the usual way of extending this to a sigma algebra, first extend it to outer measure on P of x cross y. Outer measure. and then restrict it to the measurable subsets. Restrict eta star to A cross B, call it eta, and then it is easy to verify that it is a measure. But yes, as mentioned in one of the lectures, notice that, oh yeah, this cross and this cross is of course same. So, as mentioned in one of the lectures, this A cross B, it is not the set of all measurable subsets. Not the set of all measurable sets. And I think one of the examples was done during the lecture, so I will not go into that. What is important in all this is there is a natural way to calculate the measures of these sets using what was called in the lectures as the sections. So if you go back to this rectangle here, perhaps I'll draw one more. Let us look at this rectangle E cross F. Now, to measure the area of a rectangle, the natural way to do it is, let us look at this line here. Whatever the length of the line, this is precisely the breadth. Right? So this line, let us move throughout the rectangle, and then that total movement, it would give the area equal. Or what I can do, let us start with a horizontal line, and let us move it vertically. The total movement will again give me the area of E cross. Now intuitively, what is this line? This line is x is equal to some constant. On the other hand, this horizontal line, this is y equal to some constant. So using this sort of intuitive notion, we can define sections Ex, which is the collection of all those y's in y's, such that x comma y is inside E. So notice that this is precisely if the set is not really of the form of a rectangle, but the set is something like this, then the x section of E is, look at this line, x equal to constant. Wherever it intersects E, that is my Ex. Because these are precisely the points on Y. So, or rather, this is not the section. This is the section. This is my Ex. On the other hand, similarly, one can define Ey. So, let us look at y equal to constant, maybe this line, y equal to constant. Look at this thing where it intersects E and project it on X. This is my section of Y, Ey. So let me just write the definitions. All those x in X, such that xy is in E. And perhaps the most important result in all of this construction is that for measurable subsets inside A cross B, we can measure the measure of E using these sections in the following way, that we have seen that x going to measure of Ex and y going to measure of Ey. So, these two functions are measurable functions. Moreover, they are non-negative by definition, so that is also not a problem. Non-negative measurable functions. And therefore, we can think of defining the integral of these functions. Suppose let me call this as fx and let me call this as gy. So one can, oh yeah, I mean to say f means just f, not fx, and g as this function. Then one can think of integrating f with respect to x, and one can think of integrating g with respect to y. And first one, the integral is on x. The second one, the integral is on y. What we proved was both of them are equal, and in fact, they are equal to the product measure of E. So, this is the remarkable fact that by moving these line segments slowly throughout, the horizontal line segments throughout E and the vertical line segments throughout E, one can get the measure of E. But of course, once we start moving the horizontal line segments, the length of that line segment does not remain same. For example, even here, this horizontal line segment has a different length, but if I start with this horizontal line segment, it is in fact a union of two line segments. So in general, this is just a function. It may not be constant, these are x and gy's. But overall, both the integrations are same and they give us the measure of E. Okay. So, but here, one of the basic assumptions is that both these measures are sigma-finite measures. Otherwise, we cannot proceed. If one has gone through the proof of this, we use the notion that first we prove it for finite space, measure spaces, where we assume that both measure of x and measure of y are finite. Next, we go to sigma-finite measure spaces, where we can break the whole space into disjoint union of finite measure spaces. And in each of them, we know the result, so we can extend it to the whole space. But in general, without the assumption of sigma-finiteness, we cannot do it. X and Y are sigma-finite spaces. So one really expects a counterexample when we consider that at least one of them is not sigma-finite space. So let us look at that example first, and then we will proceed to looking at other examples. Let us consider x and y both as the set of real numbers. But now what I will do is I will consider two different sigma algebras on R. I will consider two different measures on R. One of them will not be sigma finite, and we will see that these integrals themselves, they are not equal. Forget about being equal to the measure of E. These integrals themselves will not be equal. So let us look at the sigma algebra one, that is A, as the Lebesgue sigma algebra, or okay, maybe I'll not take R because it is really a big set. Let us consider 0, 1. This is a finite space in general. If we take the Lebesgue measure, it is a finite measure space. Therefore, it is sigma finite automatically. Let us have the first sigma algebra as the Lebesgue sigma algebra of measurable sets. This is Lebesgue sigma algebra. Let us consider another sigma algebra as the power set of 0, 1. So this is the finest sigma algebra one can have. This is the largest one, right? Power set of 0. Now what I will do is, of course, the Lebesgue sigma algebra requires that the measure on it is the Lebesgue measure. But on power set, one can define many different measures. One of the measures which I am going to define is called as the counting measure. So on A, keep the Lebesgue sigma algebra, keep the Lebesgue measure. But on B, define the measure mu from P01 to 0 infinity as mu of a set A is number of elements in A whenever A is finite, and plus infinity if A is infinite. So, well, let me just write the notation. This mod A means, this is not mod A in the sense of absolute value. It means the number of elements in A. And notice that I am saying number of elements and not the cardinality. So this quantity is defined only when A is finite. If A is infinite, we cannot say how many elements are there inside it. Okay. All right. So the first question is, we know that this A is sigma finite. That means if you look at the real line, or even not the real line, just 0, 1 with the Lebesgue measurable sets and with the Lebesgue measure, this is a finite measure space, therefore a sigma finite measure space. So no worries here. What about B? The question is whether B is a sigma finite measure. Indeed, it is not a finite measure because whole of 0, 1 contains infinitely many elements. So the measure of 0, 1 is infinite. So it is not a finite measure space. But whether is it sigma finite, that means can we decompose it into countably many spaces, each of which is a finite measure. Is 0, 1 with the power sigma algebra with the counting measure sigma finite. And yes, I never really mentioned it here. Let me write it. This is called the counting measure. Because we are really counting the number of elements. And one can easily check that this is a measure. If one wants to see it clearly, let us look at this. If A is empty set, then it has no elements. Therefore, number of elements inside it is 0. So measure of empty set is 0. And if we start with a countable family of disjoint sets, then either that countable family union will be having infinitely many elements, in which case, anyway, both the things are infinite. If not, then what will happen is all these sets are finite, and moreover, after some stage, either the sets are repeating or the sets are empty. So in that case, also the total number of elements is the sum of the number of elements of these individual sets. So this is a measure. It is easy to verify. I will not do it here. What is more important is the question whether this measure space is sigma finite or not. So to understand the sigma finiteness, suppose it is. Suppose 0, 1, P0, 1, and the counting measure is sigma finite. Then there exist countably many subsets of 0, 1 with measure of xn finite and xn intersection xm is empty for n not equal to n, such that union of all these xn's is all of 0, 1. Now, since this is a disjoint union, measure of 0, 1 can be written as sum of the individual measures, yeah, measures of xn's, and at the same time, well, okay, so there is a subtlety. Each of this is finite, does not imply that this does not imply that measure of 0, 1 is finite. Because, well, what if everything is 1? So in that case, this sum is infinite. So that is not the argument we are going to give. The argument which we are going to give is that since the measures of xn is finite and we are talking about the counting measure, it means that each of the xn is a finite set. Is a finite set. And therefore it is a countable set. But that would mean union of 1 to infinity, xn's, this is a countable set. Since countable unions of countable sets are countable. Countable unions of countable sets are countable. Okay. But we are claiming that it is equal to 0, 1, the interval 0, 1, which is not countable. But 0, 1 is not countable. And this gives a contradiction. Therefore, this measure space is not sigma finite. So we have concluded finally that 0, 1 with the power sigma algebra and the counting measure, it is not sigma finite. Okay, if it is not sigma finite, then let us start constructing the counterexample which we desire. So we want to show that this equality may not hold if both the things are not sigma finite. Right? So let us consider a very special set which is called the diagonal set in the product. So okay, I'll write the general definition, that would be better. Let x and y be sets. Of course, non-empty sets, because if it is empty, then the product Cartesian product is automatically empty, and then there is nothing to study there. So let X and Y be non-empty sets. The diagonal set of X cross Y is defined as D, and it is given by, look at all those pairs inside X cross Y for which both the coordinates are same, sometimes also denoted by delta. Well, now this is like the definition is true for any like any sets X and Y. We want to specialize this to our case when X and Y both are 0, 1. So consider D, that is all those pairs in 0, 1 cross 0, 1, such that Y is equal to X. So how does this look like? And okay, why is it called a diagonal first of all? So this is 0, 1, this is 0, 1. So 0, 1 cross 0, 1 is this square. And if I look at X equal to Y line, that is precisely this line, which is the diagonal of this square. So this is our D. Right. Now we want to see what is the measure of D. So first of all, well, the measure here would be 0 because it is a line. So that is not a big deal. But let us see whether we can compute it using these integrals. So for that, let us look at dx. That means the section of D on X. That is the collection of all those y in 0, 1 such that xy is in D. But there is only one such y, that is singleton X. Let us look at dy. That is all those x in 0, 1 such that again xy is in D, which is again singleton y. Because what I am saying is, look at this line. Look at this horizontal line here. So here y is fixed. Y is fixed. Where does this intersect D? It only intersects at one point, which is y. On the other hand, I am also saying that look at this vertical line where x is fixed. Look at where it intersects this purple line. It again intersects only at one point, and that value is x. So therefore, in this case, the sections of D are actually singleton sets. But the thing is that when I say dx, this is contained inside some different measure spaces. So let me write it properly. So dx is inside the y set. That means it is contained in 0, 1 with the power sigma algebra and the counting measure that I have defined. On the other hand, dy is inside 0, 1, but here the sigma algebra is the Lebesgue sigma algebra of 0, 1 with the usual Lebesgue measure. Therefore, what is the measure of dx? Measure of dx is measure of a singleton set. Measure of a singleton set is 1 because it is a counting measure. But the measure of dy is length of the singleton set, which is 0. And y. Notice that this is true for each x. This is true for each y. All in all, what we are saying is that these functions f, which takes x to the measure of dx, and g, which take y to the measure of dy, they are basically constant functions. So f at any x is 1, g at any y is 0. Therefore, integral of fx d lambda x. So notice that this was our x, right? X was the first one with the counting measure. So let me not write it x because it is confusing. 0, 1. This is integral of 0, 1. Now fx is 1, so it is just d lambda x, which is 1. On the other hand, integral of gy on 0, 1 with the counting measure, this is integral of 0, 1, but the function is now 0, which is 0, and therefore these two are not equal. So what we concluded is that in general, integral of, basically integral x, integral y, chi e x y dy dx. This is not equal to integral y, integral x, chi e x y dx dy. In the notation of the last lecture, if one has seen. That means we cannot look at the sections if in general, so for non-sigma-finite spaces. These two, I mean, taking the sections and taking their integrals may not give us the same measure. So, therefore, all that construction, whatever we have done, it is valid only for those measure spaces which are sigma finite. This was one point that one needs to understand. Now let us move on. Let us go to something. Let us look at some examples that will help us solve the quiz questions or the assignment questions, if you call them that. So again, I will do one example which emphasizes the importance of the sigma-algebra technique. And I will give you a hint that some of the questions in the assignment can be solved using sigma-algebra technique. So rather than going for all the computations that one might do, of course, they can be solved with the regular computations as well. Only thing is that that path is too long and tedious. So one can try doing that using sigma-algebra techniques. If one follows through, then it is much easier. So let us look at one example where this importance is seen very clearly. What I want to do is, given a set in the Borel sigma algebra of R, this is the Borel sigma algebra. So that is the smallest sigma algebra containing all the open sets. Smallest sigma algebra containing all, or rather I would just say open intervals. Now, given a set inside this Borel sigma algebra, let us define a set SE as, look at all those xy's in R2, that means R cross R, such that x plus y is inside E. Now, one may ask, first of all, what does this set mean? How does this set look like in R2? So let us look at a few examples where we can construct this SE in a very particular fashion, and we can look at it as some diagrammatic representation of maybe lines, points, rectangles, or anything of that sort. So first, let us look at a singleton set. Let us look at singleton 0. Now, when I say that x plus y is inside singleton 0, it means x plus y is equal to 0. So SE is, look at all those xy in R2 such that x plus y is equal to 0. So this is basically a line, and it has slope -1. So it looks like this. This is S of singleton 0. Clearly, it is measurable in R2 because it is a closed set. It is a Borel set in R2. So one of the observations, let us make it here. Clearly, SE is a Borel set. What are Borel sets in R2? They are all, again, generated by the open sets of R2. So since it is a line, it is a closed set. Closed sets are Borel sets, so no issues. Let us look at one more thing. Let us look at perhaps 0, 1, open interval 0, 1. Now, what does SE look like? SE looks like, look at all those points xy in R2 such that x plus y is inside this open interval. What does it mean by inside this open interval? It means 0 is strictly less than x plus y is strictly less than 1. Or what is the same? I can write or look at all those xy in R2 such that minus x is strictly less than y is strictly less than 1 minus x. So here, Notice that the choice of X is free, just as was in the previous case. So choice of X is free and it puts a restriction on Y. Restriction on Y. So again, let us try to draw it. How does it look like? So again in R2, 0, 1 interval, it will look like something here, 0 to 1. Let me draw the same interval on the y-axis as well. So it will start here, it will perhaps end here with a vertical line. Now, let us start fixing some x's. Let us fix this first. At 0, what are all the points for which, if x is equal to 0, we have 0 less than y less than 1. So everything on this green line is inside SC. Now, let us fix 1. If x is equal to 1, then minus 1 is less than y and y is less than 0. So somewhere here, and then this vertical line is inside SC. This vertical line is inside SC. But if we fix half, that means minus half is less than y and y is less than half. So half from here to here. So this vertical line is inside SC. And if I fix some other x, say suppose I fix minus 2, then this would say 2 is less than y and y is less than 3. So somewhere I should have drawn it bigger. But nonetheless, one can imagine this vertical line. So all in all, we get something like this. Something like this. And so on. And notice that these orange lines are not included. Orange solid lines not included. Everything inside this is our AC. So this is a strip. This is an infinite strip. In fact, it is an open infinite strip. Therefore, again, it is in the Borel sigma algebra of R2. Again, SE is a Borel set. And we have seen that in general, sigma algebra generated by a collection cross another collection is contained in the smallest sigma algebra of the product. Therefore, the Borel sigma algebra of R2 is contained in the Borel sigma algebra of R product Borel sigma algebra of R. So in particular, what we have seen is, at least for these two choices of E's, the sets are inside BR cross BR. The question is, given any Borel set inside R, can I say that SE is inside BR cross BR? Question. Given a set E inside BR, can we conclude that SE is inside BR cross BR? To answer this, let us apply that sigma algebra monotone class technique. What we'll do, let us look at the collection of all those sets inside BR for which the property holds. So let P be defined as, look at all those sets, the Borel sets of R, such that the set SE is inside BR cross BR. Yes. I mean, this is not the Cartesian product, the sigma algebra generated Cartesian product. Okay. Now, so first of all, the first question should be, is this set non-empty? This set is non-empty because I know, because I have found in fact two examples which are inside this class. So singleton 0 is inside P and this open interval is inside P. In fact, one can easily see that all singleton sets are inside P. because they are just lines. The SCs are just lines, and being Borel sets, they are inside BR cross BR. Okay. Now, what we want, first one thing is clear that P is anyway contained in BR. So if I want to prove that it is equal, it is enough to prove that it is a sigma algebra and it contains all open sets, or it contains all open intervals. So let us start proving it. First, let us prove that it contains all open intervals, and then we'll prove that it contains. I mean, it is a sigma algebra in itself. So let us take E as an open interval AB. Just a minute. In R. So it is an open interval. Now, what about SE? SE by definition, it is all those xy in R2 such that A is less than x plus y is less than B, which is, well, xy in R2 such that A minus x is less than y and y is less than B minus x. Now the question is how to prove that this is inside BR cross BR. One way is, let us prove it is an open set, and therefore it is a Borel set, and Borel sigma algebra is contained inside BR cross BR. Therefore, SE is inside BR. So, therefore E is inside BR. So to prove this, that SE is an open set, let us start with some xy in SE. Again, let me draw a diagram that would be easy to visualize, and let us fix a set, this open interval AB here. Then we have seen that the set SE actually looks something like this strip. This is our SE. And the orange lines are not included. Orange lines not included. So boundary basically, it is not included. Let us look at some point xy here. What we can do, look at the distance of this. Okay, let us first mention what these lines are. This line says y is equal to b minus x. This is a minus x. Y is equal to a minus x. Let us look at this distance. Let us call it as d1. Let us look at this distance. Let us call it as d2. Whichever is smaller, let us draw a sphere, or rather a ball of that smaller radius around xy. Then this will be completely contained inside this orange strip. So that is the general idea. So let d1 is equal to distance of the point xy with the line y is equal to b minus x, and d2 be the distance of the point xy with y is equal to a minus x. So I leave it to you to compute these distances. Compute these distances, and let us look at the following set: b of xy comma minimum of d1 d2, which is the collection of all uv in R2 such that x minus u square plus y minus v square, this is less than minimum of d1 d2 whole square. So this is the open ball which contains xy as the center, and the other elements cannot go beyond minimum of d1 d2. So therefore, by simple geometry, or one can even prove it analytically, this, if I call this just as B, then B is contained inside SE, which means SE is open. Because the definition of open sets is each point must have open ball space around it inside SE. So you take any point in SE, we should be able to find a ball which contains that point and it is contained inside SE. So we can do that. This is the construction. This is the way to do it. Therefore, SE is open. Therefore, SE is a Borel set, and hence SE is contained inside BR cross BR. That is to say that all open intervals, are in this collection P. Now it is enough to prove that B is a sigma algebra. Now to prove P is a sigma algebra, we have to prove three things. One is it should contain empty set and whole space, but that is true because they are intervals in themselves. They are open intervals in that. And the next thing we need to prove is that P is closed under complements and P is closed under countable unions, countable disjoint unions. So let us start proving it. So first one is very easy, that empty set and all of R are inside P since they are open intervals. Let us start proving the second one. That means if E is inside P, then E complement is inside of P. So we need to see whether this is true. So one way is, let us look at S of E complement. That means all those x, y's in R2 such that x plus y is inside E complement. But what does it mean that x plus y is inside E complement? It means that x plus y is not inside E, and therefore the pair x comma y it cannot be inside SE. So what I mean to say is, start with xy in SE complement. This is same as saying x plus y is inside E complement, which is same as saying x plus y is not inside E, which is same as saying x comma y is not inside SE. But the last one is same as saying xy is inside SE whole complement. So therefore, SE complement is actually equal to SE complement. And since BR cross BR is a sigma algebra, and E belongs to P, this automatically implies SE belongs to BR cross BR. We also have that SE complement, which is S of E complement, this is inside BR cross BR. So notice that here we did not use any type of computations. We only concluded everything from our knowledge of sigma algebra. So therefore, E complement is also inside P. Now the third thing we need to check is that if En is a sequence in P with En intersection Em is empty for n not equal to m, then union of Ens is again inside P. So we need to see this. So for this, let me just denote this as E. That would be a better thing to do. Now let us look at SE. This is the collection of all xy again in R2 such that x plus y is inside this union ENs. But what do we mean by something being inside union is that it is inside at least one of these sets. But one of these sets that is inside P, so those S of ENs are inside P, so union of S of ENs is again inside BR cross BR. Did I say P? Oh, yeah, I meant to say S of ENs is inside BR cross BR. So let us write it. XY is inside SE. This is same as saying x plus y is inside this union, which is same as saying there is some n such that x plus y is inside En. But then this is same as saying there is some n such that x comma y is inside Sen, which is same as saying x comma y is inside the union of Sens. Therefore, we have proved that SE is equal to union of SENs, which is inside BR cross BR. Since all those ENs are inside P. Therefore, E is again inside P, and hence P is a sigma algebra, which would imply that P must be equal to BR, because BR is the smallest sigma algebra containing all open intervals. P is a sigma algebra contained inside BR, which contains all open intervals, so they must be equal. So what we have essentially proved is our conclusion is that given any set E inside BR, the set I have written SE, the set SE, that is all those points in R2 for which x plus y is inside E. This is an element of BR cross BR. So one can ask a question whether BR cross BR is same as B of R2. That we will not discuss at least today. It is one of the assignment questions. We want you to try it yourself. And if you are not able to do, we can discuss it next time. Okay, so this was one of the things. Now, one more thing which is worth emphasizing is that we always talk about integrations as area under curves. But till now, we are not able to look at it properly. There are two reasons. One is that Riemann integration, although it gave a very nice interpretation of integration as area under curves, it was valid only for closed and bounded intervals. It was not even valid for those measure spaces which are of finite measure, but they are not intervals. So Riemann integration doesn't give us that. Lebesgue integration, as far as whatever we have studied till now is concerned, it does not give us any geometric interpretation unless we restrict it to the space of all Riemann integrable functions. But that is already known to us. So now we would like to look at the integral, understanding the integral of a non-negative measurable function, or non-negative integrable function rather, because if it is not integrable, then that area is finite and infinite and all those things we don't want. Of a non-negative integrable function as the area under the curve. Or the curve is not a proper thing to write, area under the graph. So there are many things that need to be addressed here. First of all, what do we mean by area? What do we mean by under the graph? Right? What do we mean by graph is another question, but that is easy to answer. It is the collection of all points x comma fx as x varies in the domain. So what we want is, let us look at a function from x to 0 infinity and assume that f is in L1. X is of course a measured space. We want to look at the graph of f. So graph of f is defined as, look at all those xy in x cross r or x cross 0 infinity, whatever is the codomain, such that y is equal to f of x. So in general, it may look something like this. This is our reference. Now we want to visualize this part. Now this is the area under the curve. We want to visualize this as the integral of. This is our question. Some different color. This is called the graph. Okay, for this, what I'm going to do is I'm going to define two sets of, well, they are not very intuitive sets, but that construction is important in whatever we are going to analyze. So one might ask why I am doing what I am doing, but that will be clear in a moment. So let me just write it first. Let us look at E lower star f as uh, all those xt in x cross r such that t is non-negative. I could have written r like 0 infinity instead of r, and t is strictly less than fx. And let us write E upper star f as all those xt in x cross r for which t is non-negative, and now t could be equal to f. So what is the difference? This only the blue shaded area, that is our E lower star x. E lower star f, and the blue area along with the green area, that is E upper star. So why I have done this? Because now I can write the graph of f as in terms of this E lower star f and E upper star f, and I expect that both these areas are going to be same because the graph is really one dimensional. It does not take any area. It has length, but it does not take any area. That is what we expect. We don't know whether it is true or not, but then it is easy to see that the graph of f is equal to E upper star f difference E lower star f. That means look at all those xt such that 0 is less than t less than or equal to f of x, and t is not strictly less than f of x. It means it has to be equal. So this is one major observation. Now, sorry, just a moment. Let us correct. Right. Now I'm going to prove a sequence of results regarding all this. So I will name them like this. The first result is this, that let Fn be an increasing sequence. Be an increasing sequence. Okay, notice that all these definitions do not require measurability of F. Does not require measurability of F or even integrability of F. Like we can just define this E lower star and E upper star of F. They can be defined for any F. And in fact, for any F, graph of F can be written like this. So all these definitions and conclusion, it is independent of the measurability. Let us, so in this result, I'm not going to assume that Fn is increasing sequence of measurable functions. I'm just going to assume that it is an increasing sequence. That means Fn at x is less than or equal to Fn plus 1 at x for every x. And let Fn converge to a function f pointwise. Then the first claim I am going to make is about E lower star f. That means look at all those xp's in x cross r such that 0 is less than or equal to t is less than f of x. This is strictly less than, remember. So since, okay, let us start with some xt in E star f. This is same as saying 0 is less than or equal to t, strictly less than fn. But since t is strictly less than fx and fn is an increasing sequence that converges to fx, therefore there is some n naught such that for each n bigger than or equal to n naught, yeah, this means fx minus t is positive. Fn at x is strictly less than, oh, yeah, actually I must write fx minus fn of x is strictly less than t. So no. What I want p is less than fnx, and this is less than fx. Yes. So I'm not going to use this fact. I'm going to use the fact that since fn increases to f of x is actually the supremum of fx. So since t is strictly less than the supremum, it is not an upper bound. Therefore, we can find a number after which everything is bigger than t. So in particular, therefore xt is inside E star Fn for some n. Therefore, xt is inside union of E star Fn. That means I have just proved that E lower star f is contained inside union of E lower star Fn. But notice that if xt is inside E lower star Fn, then 0 is less than or equal to t is strictly less than fnx, but fnx is anyway less than or equal to f of x. It means xt is already inside E star f. Therefore, this union is anyway contained in E star f. And hence, these two are equal. Therefore, E lower star f is equal to the union E lower star f. And let us call this as result B. Okay, now let us look at result B. Let fn's, yeah, we have been using essence from x to 0 infinity. Let these be measurable simple functions. Or maybe we don't require a sequence here, just s, a measurable simple function. That means s can be written as I from 1 to n, ai, chi capital AI, where this ai comes from this sigma algebra of measurable subsets of x. Ai intersection aj is empty for I not equal to j, and union of aij is all of x. This is a finite union. Okay. So what can we say about E lower star s? E lower star s is all those xt's in x cross r such that 0 is less than or equal to t is strictly less than s of x. But for every x, there is a unique I between 1 and n such that x is inside ai. Therefore, for every x, there is a unique I between 1 and n such that 0 is less than t is less than small ai. And therefore, what I can say is that x comma t is inside this union, I from 1 to n, ai cross 0 to ai. Because, once we start with anything here, this is less than ai for some ai, and for that ai, small x is inside capital AI. Therefore, E lower star s is contained in this union. But this union is anyway contained inside E lower star s because of the same fact that ai cross 0 ai that has all those x comma t such that x is inside ai and t is less than ai. So by definition, the other way around is true. This is inside E star s. That is, E star s is equal to the finite union of ai's cross open interval 0 ai's. So sorry. this. Let me just mark this. So what does it mean? So if X A mu is a measure space, and let me write it B here, and S from X to 0 infinity is a simple measurable function, then E lower star S is inside A cross the Borel sigma algebra of R. So why is that so? Is because this is inside A and this is inside the Borel sigma algebra. So the Cartesian product is inside the sigma algebra generated by the individual Cartesian products, and this sigma algebra is closed under finite unions. Therefore, E star S is inside this sigma algebra. Okay, so this is the next result. Now, what we want to do is we want to do this for any non-negative measurable function. And we have already done it for simple functions. So it is easy to see that for any non-negative measurable function, it must hold. So let us look at the third result. That is, let f from x to 0 infinity, let this be a measurable non-negative function. So I'm not writing non-negative because I am already writing 0 to plus infinity. So that non-negativeness is already written in the hypothesis. So since it is a non-negative measurable function, there is a sequence Sn of simple measurable functions, such that Sn's are increasing and Sn converges to F. But then by this result A, E lower star of F is union of n from 1 to infinity, E lower stars of Sn's, and by B, E lower star Sn is inside A cross the Borel sigma algebra of R for every n. Therefore, E lower star F is inside A cross the Borel sigma algebra of R. And this is our third result. That for any non-negative measurable function, this E lower star F is inside the sigma algebra generated by the rectangles of A and BR. Okay, now we are almost there. We just need to see what about that upper star thing. So that is our next result. So E upper star F, one can write it as intersection of 1 to infinity E lower star F plus 1 by n. And why is that so? It is easy to check. So if 0 is less than or equal to t is less than or equal to f of x, this automatically implies 0 is less than t. It is strictly less than f of x plus 1 by n for every n, which means E upper star F is contained inside this intersection. On the other hand, if for every n, t is strictly less than fx plus 1 by n, and of course it is bigger than or equal to 0, then t is less than or equal to fx. That is because if t is strictly bigger than fx, then we can find one n for which that fx plus 1 by n is between them. So that is not going to happen. So therefore this intersection is again contained inside E star f. Therefore E star f is equal to these intersections E star f plus 1 by n. This is our result D. And what we can conclude from here, maybe I'll write it as D prime, is that if f from x to 0 infinity is a measurable function, then E lower star f is inside A cross B, and E upper star f is also inside A cross B. That is because if f is a non-negative measurable function and g is a non-negative measurable function, then their addition is a non-negative measurable function. So each of these sets are inside A cross B R. So their intersection is again inside the sigma algebra. So all of them, this E lower star f, E upper star f, are inside the sigma algebra. So their difference is inside the sigma algebra. So the next observation is that the graph of f. So I'll continue this. So f is already a non-negative measurable function. E upper star f difference E lower star f. This is inside A. The sigma algebra generated by A cross B. Not the usual B, Borel sigma algebra of R. Okay. So now we are done. Now just we need to look at whether we can really see this. So as I have mentioned earlier, if I have this graph, this is our fx, and if I look at everything on and below this curve, this is our E upper star f. I know that it is a measurable set, so I can talk about its measure in the product sigma algebra. Now this is our x and this is our r. So I can talk about mu cross lambda of E upper star f. And assuming that x is a sigma finite measure space, R is already a sigma finite measure space, this must be equal to integral of x, integral over x, the measure of E upper star of f x section dx. So again, here we are using the fact that integral x, integral y, pi E x y dy dx is measure of E in the product sigma algebra, and this is also equal to integral y integral x pi E x y dx dy. So the first one I have already done because this is what? This is precisely lambda of, or maybe, yeah, this is precisely lambda of E star f x. Whichever you want to consider x and y, doesn't matter. But yeah. So now we just need to see what is this E star fx section. So E star f x section, it is equal to, this x section will be in R. Look at all those t such that x comma t is inside E star f. But what is the definition of being inside E star f? It means that 0 is less than or equal to t is less than or equal to f of x. But this is the interval 0 comma f of x. Therefore, the measure, the Lebesgue measure of E star fx, this is equal to fx. And mu cross nu of E, well, not E, E star f, this is equal to integral of fx d mu, d lambda x, d mu x. On the other hand, one can check the other way equality also. We don't need to check it here because that has to be true, but still let us check it. Another way I can do it is that mu cross nu of E star f is equal to integral over r, or rather we are not taking okay, it doesn't matter, integral over r nu of oh, sorry, again the problem is that measure is the Lebesgue measure, so rather than writing nu, let me write lambda, and this is mu of E star f t d lambda t. Yeah. So again, one might very well see this. Okay. So yeah, these two must be equal, right? So what I can say is that, although it is not easy to see. Okay, anyway, let us not write it. It's unnecessarily time consuming. Let us not write it. What one can check is, what about this lower star? E lower star f. Again, this is integral x, measure of E lower star f x d mu x, which is integral x, measure of all those t for which 0 is less than or equal to t, but t is strictly less than fx. This is also an interval. So again, that is going to be fx. So therefore, what we conclude is that the Lebesgue formula for integration, conclusion, the Lebesgue's recipe of integration has the geometrical interpretation as the area under the curve of area under the graph of the function, as the area under the graph of the given function. So yeah. So with this we sort of conclude. Yeah, there was one question in mail which I would like to mention here now. So the question was as follows. We have already seen that S of C cross D is contained inside SC cross SD, but the equality is in general not true. In general, the equality is not true. So why is that so? Is because S of C cross T is a solid sigma algebra containing rectangles. On the other hand, SC cross SD, it is generated by two sigma algebras themselves. So the problem is, if we start with a bigger set, one may expect that we get a bigger sigma algebra. So to visualize this, to get a counterexample that the equality may not be true, what we can do, let us look at this set. X is again any non-empty set. And why in the lecture we have considered this 1, 2, 3, 4. But one may consider other sets, for example, 1, 2, 3, or just 1, 2, or anything else. The idea is going to be this, that let us consider the collection empty. I mean, the collection containing only the empty set, not the empty collection. And let us consider this empty 1, 2, 3, 4, and whole of y. So D itself, it becomes a sigma algebra. Why is that so? Because you know, empty set is there, whole space is there. It is closed under complements because the only complements possible are complement of 1 2 is 3 4, complement of 3 4 is 1 2, complement of empty set is y is empty. So all the complements are there. It is also closed under countable unions because we have only a finite collection. So we have like finite unions are there, so countable unions are also there. So it is a sigma algebra, but this is not a sigma algebra. Not a sigma algebra. That is because the whole space is not there. So what is sigma algebra generated by C? Notice that C is a semi-algebra, right? Or no, no, it is not a semi-algebra as well because the whole space is not there. But how to generate a sigma algebra? Let us put in all the missing things. So S of C, that is the sigma algebra generated by C. So first of all, notice that C must be inside S of C, which means empty set is inside S of C. Now, since SC is a sigma algebra, we want that X must be inside S of C. So the question is here, whether SC is just two sets, whether this is equal to empty set and X. This is indeed a sigma algebra. That is not a problem. We have already seen this. It is a sigma algebra and it contains C. Moreover, there is no proper sigma algebra contained inside SC which also contains C. Also, no proper subset of P comma X is a sigma algebra. Therefore, this phi comma X is the smallest sigma algebra that contains C. Now, once this happens, then SC must be equal to this. Therefore, SC is equal to phi comma X. Okay. Now, what about C cross D? That means the Cartesian product of elements in C and Cartesian product of elements in D. So, in general, they are rectangles where A comes from C and B comes from D. But there is only one set inside C, which is the empty set. So, empty cross B, where B varies in D. But this is just empty. And we have seen that the smallest sigma algebra generated by singleton empty is the two sets X and the whole space. Therefore, S of C cross D is phi comma X cross Y. On the other hand, SC cross SD. So this is not the sigma algebra generated by SC cross SD. It is the Cartesian product of SC and SD. So this is again A cross B, such that A varies in SC and B varies in SD. But since D itself is a sigma algebra, it is SD is D itself. So it is A cross B, such that A varies in this two element set P comma X and B varies in D. So there are various possibilities of B here. In particular, of course, the empty set will be there. The whole space X cross Y will be there because X is inside this two set Px and Y is inside D. So it will be there. But there is also this set Phi cross 1, 2, X cross 1, 2 and X cross 3, 4. This is also there. Whether or not it is sigma algebra, it is always contained in the sigma algebra generated by these two. It may be equal in this case. But what we do observe is that S of C cross D is strictly contained in SC cross SD. So this provides us a counterexample we were looking at. So, all right. If you have any questions, I'll again give you 1 minute to ask. YouTube audience can ask me on the chat, the live chat, and then we will stop. Okay, so if there are no more questions, let us stop here, and we'll meet next week on Friday, same time, to get the discussion of week 11 done. So, thank you.